Hello and welcome to CS350 episode number 11. I'm your host, as always, Leslie Eiston. Now, on today's episode, we're going to do things just a little bit different. So normally at this point in the course, we would spend about 30 to 45 minutes talking about how do you implement assignment A2a. And then we'd go on about our regular business. And then in a couple weeks, we would talk about assignment A2b, and we'd spend another half an hour to 45 minutes talking about that. What I've decided to do on today's episode is combine the discussion of both assignment A2a and A2b into one single discussion. And that way you will be completely prepared to do both of the next two assignments, which for the record are both dealing with processes and system calls. And then in episode 12, so our next episode, we'll start our new topic of virtual memory, which will last us about 4 episodes or so. We'll see how the timing plays out. All right, so before we do that, let us talk about the OS of the day. Now, today is a very special episode of the OS of the day. We're talking about one which some of you may have heard of and some of you may not have. It's called Alto Executive. Now, Alto Executive is a product of a very famous place known as Xerox PARC. This was released in 1973. And the computer this was released for was a product also of Xerox PARC called the Xerox Alto, which for all intents and purposes, you could consider that the Xerox Alto in 73 was actually the first personal computer. Because if you look at the size of the Alto versus all of the other computers at the time, the Alto, which is pictured down here in the bottom, was a really small filing cabinet sized computer. It had a traditional QWERTY keyboard, and you can see here there's even a 3-button mouse. Now, it also had another keyboard as well, a 5-chord keyboard. So it had traditional peripherals, traditional keyboard. It was a very modern-ish size, a bit big by today's standards, but the one that's sitting behind me is pretty big too. So this was very much one of the very first PCs. Now, what is Xerox PARC? So Xerox PARC is one of the most famous computer research labs in the world, and you can thank them for things like object-oriented programming, camel case, Ethernet, a large number of different inventions over the last 40 or 50 years have come out of Xerox PARC. Now, what does the PARC stand for? Are they like referring to some kind of magical playland for computer scientists? I mean, in a way, I suppose. Really what they're talking about is PARC stands for Palo Alto Research Center. So this is in California. If you guys are ever able to go to California, due to the whole visa thing that's going on right now, this is a place that still takes interns and would be very, very valuable to have on your CV. So just keep that in the back of your mind. Now, what about the operating system itself? So the exec operating system had Ethernet and LAN support, and they actually had little LAN parties with these machines at Xerox PARC, playing various different little games that they had developed for it. This implementation also popularized camel case. It had all of the typical things you'd expect an operating system of that time to have. But one of the unique things that Executive did is, well, it had a mouse-operated GUI. It actually had like a desktop environment, and I'll show it to you in a moment here. And in order to permit you to have that instantaneous look and feel of a desktop environment, they had to blur the lines between user privilege and kernel privilege, which, there's varying things that you can think about that. Is that really a good idea from a security perspective, or is it just Is it okay here? And truth is, it was okay under these circumstances to blur these lines because they weren't really worried about internet security at the time, because the only computers that were on the internet were people who were your friends and also super excited to be on the internet. So the security wasn't so much of an issue here. But what they had to do was, in order to get that good performance for the desktop GUI, they actually had to permit user applications to access the hardware a little bit more directly to optimize. And that should kind of make sense to you, because if you think about all the extra work that you have to do for a system call, and we're going to go into that in even greater detail today, talking about A2a and A2b, you'll see that it's very obvious that this has an impact on performance. So at the bottom of the screen here, and you should be able to see it, you can actually see some of the icons that were used on Alto Executive. And these should look very familiar to you because this is kind of where they come from. So you've got an empty folder, you've got a document, you've got a printer, and you've even got a trash can. And then just to show you a couple more things, and yes, it was a black and white screen. And yes, on the previous page, the screen is in its correct orientation of portrait mode. Think about it this way. People were thinking of computers as kind of like a replacement for paper. So they were keeping the screen kind of in a paper-like orientation. And here's some of the screenshots from it. So we've got a system browser up here, and you can see layered windows. We've got a Smalltalk, which is a product of Xerox PARC window open. Looks like they are doing some window development. They've got an image open. Look, there's an email icon at the top, a clock, a calendar. And then this pig image over here was one of the famous test images that they have, because they had paint programs, they had video games, they had all kinds of different mouse-driven game activities for this. Now, what's particularly interesting is these machines at the time were incredibly expensive. My understanding is less than 2,000 of them were ever made. They cost something like 20,000 a piece. They were very, very expensive. So very few people could actually afford to get their hands on one, which is why so few have actually survived. And my understanding is that Steve Jobs was rather taken with them, and he spent some time at Xerox PARC getting familiarized with the system and the desktop GUI, and a lot of the macOS look and feel is apparently inspired by this operating system right here. So, cool story. All right, so what I would like to talk about now is assignment A2a. Now, I'm not sure, and I think the answer is that I have not yet posted the A2a and A2b slides yet to Piazza, but I will post them in a few minutes after this episode ends. So let's start by talking about assignment A2a. Again, these guides will be posted for you. But why you have an assignment called A2a and A2b is actually pretty simple. What happened was, eons ago, there was actually just assignment A2. In assignment A2, you had to implement fork, wait PID, get PID, exit, and execv. And in typical CS fashion, most people, because they're super busy, tend to leave things to the last minute. And they would implement some of them, and nothing would end up working, and nobody would ever end up getting execv to work, because most people would be stuck trying to debug, wait PID, and exit. And so in order to encourage students to get more of this working, they decided to divide it into two assignments, where you've got wait PID and exit on one assignment, and then execv by itself on another assignment. So that is actually what your next two assignments are, is implementing those 5 system calls for process management. So A2a, which is the one that's due closest to today, is fork, wait PID, get PID, and exit. Now, it's going to be very tempting for you to go ahead and start with get PID, and I want to forewarn you against that, because you can't really test get PID until you have fork working. And get PID is one of those things where if you save it to the last 5 minutes, you're going to get it to work, because it's like 2 lines of code. So let's start at the top. So remember that fork is going to create a brand new process, And that process is going to have an address space that is an identical clone of the parents, but it is actually in a separate process structure. It's too early in the morning. And then we have wait PID. And wait PID is going to permit you to pause and wait for another process to terminate before you continue. Now, one of the most important things, of course, about wait PID is you can only actually wait for your children to terminate. You can't wait for your parents, your grandparents, your grandchildren, or anything like that. Oh, you only care about your direct descendants. And then we have exit, which is going to terminate the caller, and it's going to permit us to leave an exit status code behind for the parent to tell us, did this process terminate successfully or was there an error? Now, when you're implementing this assignment, my recommendation to you is to do it in small parts. Start with fork, and don't move on from fork until you're convinced that you have it working properly. And then do wait PID and exit together. That's really important because they are very directly linked. But it's the thing that I really want to emphasize is do small bits, compile and test. Small bit, compile and test, lots of versions. Because one of the biggest problems that I see students have with this particular assignment is either race conditions or deadlock between wait PID and exit. And the actual code body doesn't take long to implement for this assignment, but trying to debug and resolve the race conditions and deadlock between wait PID and exit can take you weeks. So get started early. All right, let's start with fork. So what you're going to do is you're going to start by creating a new process structure for the child process. Fork is creating a new process, so you need to create a new process structure. Now, when you create a new process structure, you don't get an address space. So you're going to have to create a new address space for the new process and then copy the contents of the parent's address space into the child's address space. And then, of course, once you've populated the child's address space, you'll attach it to the actual process itself. Once you know that's going to work, and you may not, this is where there's a little bit of freedom here. At the point where you've attached the address space to the child process, there's a very reasonable expectation that the new process is going to work. So this is where some people like to assign a process ID number to the child process and to establish the parent-child relationship. This does not mean this is where you have to establish the PID, but this is one place where you could conceivably do it. Now, the parent-child relationship, it doesn't make sense to do until this point because you shouldn't set up a parent-child relationship if the process isn't actually going to succeed. After you have set up the PID in the child-parent relationship, one of the things that you're still missing for the child process is a thread. When you create a process structure, one of the elements of it is a thread array. But that thread array is empty. And remember that a process doesn't actually run. It's the threads of the process that run. So what we actually need is we need to create a thread for our child process. And we need to make sure that the thread for the child process is going to have the exact same stack that the parent's thread has, so that the two processes will continue executing code in the exact same state from the exact same point at the exact same time. So we're going to need to be able to copy the trap frame from the parent into the child, because remember, the trap frame is where the context of the parent process is stored while we handle the system call. So we're going to need to take that trap frame and copy it down to the child. After we've done that, then we need to encourage the child's thread to start running, because it's not just going to start running and return from the kernel privilege mode on its own, whereas the parent's thread will return from kernel privilege mode on its own because the parent's thread is what responded to the exception. But the child's thread did not respond to the exception because the child's thread was just created. So we need an artificial way of returning to user privilege, and we do that with this called to MIPS user mode in the child. All right, now that probably seems like a lot of work and that you're going to have to figure out a lot of different things about the operating system. But a surprising amount of this code has actually already been implemented for you. So first off, you need to create that child process structure. You don't need to malloc anything. All you need to do is call proc create run program. And proc create run program is going to allocate the memory for the process structure, and it's going to populate those fields of the process structure that it can populate at this point in time. This is often the function where a lot of people like to assign their PIDs, and I'm going to leave that decision up to you entirely. Now, proc create run program, you are welcome to add to this function, but please do not remove anything from it. Things like setting up the VFS, which is the virtual file system, and the serial console, those are parts that the process needs access to, but they need to stay, so don't remove them. All right. One last thing about proc create run program is that it can actually fail. And if it fails, it will return null. Now, why might proc create run program fail? Well, probably one of the biggest reasons that proc create run program fails is because when it tried to allocate memory for the new process, there wasn't enough memory available to it. So you need to detect that proc create run program has returned null, and then you are going to need to return from the system call an appropriate error code that indicates that you failed to execute the fork. And this is where the application binary interface in kern include kern comes in super handy. There is an error no file. It will tell you all of the appropriate error codes that you can return from a user process. And in the case of no memory, enomem is always a good option. So make sure you're handling these error cases. All right, you called proc create run program. You've tested to make sure it actually returns something. So now it's actually time to create that address space. Now, you actually don't have to do much work here either, because there's functions in the OS already that do the majority of the work for you. All you need to do is actually create the pointer, and then you're going to pass that into a function called ascopy. And with ascopy, you're also going to pass the address of the old address space. And ascopy is going to do two things. It's going to create a brand new address space and malloc all of the appropriate memory for it, and assign it to the pointer that you've passed in. And the second thing that ascopy does is it's going to copy the contents of the parent's address space into the child's address space. So ascopy actually handles both the malloc and the copy for the address spaces. So it's one line of code, right? Not so bad. All right. ascopy, just like proc create run program, can of course return an error code. So you need to check for those error codes again. And again, this one is going to be no memory, because that's why you would get an error in ascopy typically is enomem. So make sure you're checking and handling for that. Now, once you've got that address space populated and created, you need to attach it safely to the child process structure. Now, there's no function to do the safe attachment of the address space to any random process structure, but there is a function that can attach a new address space to you, the parent. This is not what you want to do for this function, but if you look at curproc setas, it will actually show you how to safely attach an address space. And you should mimic the code here in your own implementation to attach the address space to the child process. But don't actually call this one because you don't want to change the parent's address space. You're setting the child's address space. All right. So you've got your process structure. You've got the memory allocated and the address space populated. What's next? Well, here's the point where we start talking about the process ID number. We are not going to dictate to you how you decide on these. We don't care. If you've seen an old version of these notes or an old one of the fall lectures, then you would know that we often tell you that the PIDs have to be unique. That is true. That is always true. PIDs have to be unique, and they can't be zero. Zero is special, and the reason why zero is special is because remember that fork is going to return to the parent the child's PID, and fork returns 0 to the child process. So if 0 was a valid PID, we would have no way of differentiating between this being the child process and this being the child process's ID. So we're not going to permit PIDs of 0 for any process in the system. So please only assign greater than 0. How you make these PIDs unique is entirely up to you. In previous versions of this course, we have made, or at least previous versions of these notes, they've suggested that you needed to make the PIDs reusable. That's never been the case because we don't actually have any means of testing whether you have it working or not. So you don't have to have reusable PIDs. If you want to have some global counter where you start at 1 and you just start dishing them out and keep incrementing, that's fine. And if you're sitting there like, well, what if we run out of integers for our PIDs? Okay, this is OS 161. It's a toy. Number one, no TA, no student is going to sit there and generate 2 billion processes because none of us have time for that, obviously. And number two, OS 161 would crash long before that. So reusability, don't have to do. Counter, totally fine. If you do want to do reusable PIDs, typically the way that people do that is by creating an array of all of the possible PIDs and then marking whether the PIDs are in use or not. The downside of doing this is that that array actually consumes a significant amount of space, which is going to prove problematic on assignment 3. I can tell you if you choose to do that, you don't need to use any more than 64 PIDs. You should never ever have a test run by us or by yourself where there's more than 64 processes at any given time. So 64, that can be your limit. All right. Now, another strategy I've seen people do to make unique reusable PIDs, and I want to warn you on this. It's not that it can't be done, it's just that there's a little quirk in the system, is that a lot of people will use the address of the process structure as its PID, which makes complete and total sense because that's a unique value. However, PIDs are signed and addresses are not. And you're going to end up with negative PIDs, which are not permitted. So you have to make sure that you shift. All right. So one last thing about your PIDs. Wherever you are using to implement your PIDs, whether that's a global counter or some global array of valid PIDs, it's really important that you have a lock for that counter because we could be forking multiple things at the same time, which means that there's the potential for multiple threads to be reading and writing the shared variable at the same time. So do make sure you are using appropriate synchronization primitives to protect things like a shared global counter or a shared array. Now, you'll note that we have nothing in these notes about the parent-child relationship. And that's because how you create the parent-child relationship is completely and totally up to you. But I'd like to give you a few recommendations on how you could do it easily and fairly cheaply. And the first of those is you only have one parent. Unlike the human world where you could have any number of parents, step parents and so on, you get the point. In the computer science world, we only have one parent. which means to keep track of who your parent is, you only need either the PID of your parent, so that you can look your parent up in some global process table, or you simply need a pointer to your parent's process structure. You also need to keep track of your children, and you can do that in two ways. Well, more than two ways, but two common ways I see are students keeping track of a list or an array of all of the PIDs of your children, in which case you'd have to have a global process table where you have to be able to look up the PIDs and get the process structure. Or more simply, you could simply have an array of the pointers to all your child process structures. So how you do that is up to you. But one of the biggest things and the biggest problem I see with this assignment is people forget that access to your parent and access to your children and your list of children is to be shared. And so you can have multiple threads accessing that list of children at the same time. So it's really important that you protect those with a lock. And whether you are writing to it or reading from it, make sure that you are doing it with mutual exclusion. Otherwise, implement it however you want. And don't implement a linked list structure on your own. We have a dynamic array. It's built into OS 161. Use that. Now, this is quite possibly the hardest part of fork, and that is giving the new process a thread. So you're going to create a thread you need to call thread fork. But you want to attach this new thread to your new process, not to the parent process. So if you look at thread fork, the second argument of thread fork is actually a pointer to a process. And if you pass thread fork a pointer to the child process, then the new thread that is created will be attached to the child process's thread array. So you're going to make sure that you pass the child process to thread fork. Now, what code do you want this to run? Well, we need the kernel to do a little bit of setup for the child process's thread before the child process can return to user mode. In particular, we need to set up the stack for the child process's thread. And we also need to call MIPS user mode to force the child thread to go back to user mode, because otherwise it won't. So we're going to write a kernel function called enter forked process. And I'd like to point out that such a function already exists in OS 161, and you are welcome to modify it. And in fact, you will need to modify its arguments because it is required that the signature of what you pass in as your entry point function for thread fork is a void pointer and an unsigned long. And if you try to pass anything else, it won't work. So you can modify enter fork process so that it has the matching signature here. But what does enter fork process need to do? Well, the most important thing enter fork process needs to do is it's going to need to take the trap frame from the parent and put it onto the child's stack. Okay, how do you do that? Well, you're going to get the trap frame from the parent. That's actually an argument that's passed to syscall, not syscall the architecture instruction. Syscall, the system called dispatcher, which handles the system calls inside the kernel. You'll note that a struct trap frame is actually passed there so that we can extract the values in registers A0 through A3 and the value in register V0. Okay, that's the trap frame that you need to take and put onto the child's stack. So you're going to need to pass that trap frame from syscall into sysfork, and then from sysfork you're going to need to pass it to enter forked process, so that in enter forked process the child thread, the first thing it's going to do is take its parent's trap frame and put it on its stack. Now, how do you put something on the stack? There's going to be a lot of people, and I see this every term, where they try to malloc stuff and then memcopy it over. No, 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 no. What you actually want to do is create a local variable. Local variables are on the stack. So make a trap frame structure on the stack and do a casted shallow copy. Done. And now your trap frame from your parent is on the stack. But you're not quite done just yet. There's a few more things you need to do. One of the things you need to do is you need to set up the return values for the child process. Remember that the child process did not respond to an interrupt, which means that it's not going to return to syscall and have the return values automatically set up for it. So what we're going to need to do is we're going to need an enter fork process. We're going to need to set up the child's return values ourselves. So we're going to need to set register V0. We're going to need to set register A3. And we're going to need to increment the program counter so that the system call exception is not raised again. Now, what do you put in V0 and A3? Well, if you're at the point of enter fork process, then you know that the fork is succeeding. So you need to make sure that you've set it up to succeed, and you need to make sure that fork returns 0 to the child. So I will let you figure out what those values are. Now, is that everything you need to do for enter fork process and fork? No. Here's the problem we have right now. If I directly pass the parent's trap frame as it was passed from syscall directly into enter fork process, because of how we've written the code, we think that the thread has run and it has a copy of the parent's trap frame. But in reality, enter forked process may not actually execute until the parent process has returned from fork, thereby popping that trap frame off of its kernel stack and into oblivion, which means that at the time we call enter fork process, the parent's trap frame may not exist. And so we would be populating the child's stack with absolute garbage, and we don't want to do that. So you either need to use some synchronization to force the parent to wait to return from fork until the child process has populated its stack, and I don't recommend that. The other option that you could do is make a copy of the parent's trap frame in the kernel's heap, and then pass the heap pointer into enter fork process, and after you've put a copy onto the local stack, then you can free the kernel's heap, because that one will persist until you actually free it in the kernel. Your choice how you implement that. But with that, fork is done. It's actually not a lot of code, by the way. Oh, look, more hints on the next page. This is more of the body. You'll note the last bit, which I've neglected to mention here. At the end of enter forked process, you need to force the child thread to return to user mode, and that's what MIPS user mode does. It's effectively returning from a fake exception. All right. Now, what about wait PID? Now, wait PID and exit you should implement together because they rely on each other. So remember that wait PID can only be called on a child process. So wait PID is going to need to be able to look through the calling process's list of children and determine, has this been actually called on one of my children? And it's going to need to return an error code if the process we call wait PID on is not one of our children or doesn't exist. Now, once you call wait PID on something, if that child process has already terminated, then you're simply going to grab its exit status and its exit code, and you're going to return that. If, however, the child process has not terminated, then you are going to need to sleep until the child process does terminate. Hence why you need to do this with exit, because they're going to need to go back and forth with each other a little bit here. So let's talk a bit more about wait PID. So how are you going to get a parent process to wait on a child to terminate? My recommendation is to use condition variables. So every process should have a lock, and that should be things like protecting access to the child array and so on. And then you should have a condition variable. And when a parent process notices that the child process is still awake, the parent can go to sleep on the child's condition variable. Now, that's just one way of implementing it. I've seen many, many others. I've seen people have one master condition variable where all processes that are waiting for others sleep on it. That can be made to work, but it's a really bad idea because when you wake up a process on the CV, you don't actually know if it's the process that you wanted to wake up. So you actually have to broadcast, wake up everybody, and then everybody has to recheck the condition of is the child awake or not. And then anyone who doesn't succeed will have to go back to sleep again. So one master CV can work, but it's really inefficient. It's much easier for each process to have its own CV, and you go to sleep on the child's CV. And then the idea is in exit, when the process terminates, you would call wake, or not wake, you'd call signal on your CV, and you only have to call signal because you can only have one parent, so you know there's only one person waiting on your condition variable. So in exit, you would wake up the parent, and in wait PID, you fall asleep. After you have called wait PID on a child and you've retrieved their exit status code and their exit code, you no longer need to keep any information about that child process around. You could think of it kind of in a morbid way. Think of it as you only need to conduct the autopsy once to figure out why the child died. There's no point in doing it again and again because it's going to give you the same result each time. So, some details. You're going to need the parent process to be able to check the status of all the child processes, which means that the parent process is going to need to acquire the locks of the children in order to check their status, if that's how you've implemented the parent-child relationship. You don't have to do it that way. So make sure, and the synchronization of this gets really complicated depending on your implementation. It's the number one place where I see people having either race conditions or deadlock. It's either the situation where you forgot to wake somebody up, or it's the situation where the parent is trying to check something about the child while the child could actually be modifying something about themselves, or vice versa. So really be careful about the synchronization around that. So then we want to really talk about exit now, and I'll come back to these other topics in a minute. But in exit, you might be thinking to yourself, this is where I terminate the process. Yes, that's true. This is where I wake my parent. And it's okay to signal a CV even if nobody's waiting on you, waiting on it. And this is where I delete the process. Yeah, maybe not. So here's the thing. When a process terminates, if its parent is still alive, then we need to leave the process as a zombie. That is, it is a process that is not running, but it still technically exists. So that is, we kept it around because we needed its exit status code and its exit code. Now, what some people I see do is they destroy things like the address space and they move the process to like a not running state, and they'll have like a Boolean in the process structure that indicates whether it's dead or not. And they'll set that dead flag to dead inside of exit if the parent is still alive. And then when they wake the parent, if the parent then calls wait PID, it would check that dead flag in the child, and if the child was dead, it would grab the information from the child process it needed, like the exit code and the exit status, and then it would finish the deletion of the child process. That's one way that you can handle deleting the processes. Another thing that I've seen, but it takes a little bit more work, is people will create a separate structure to hold the remnants of the children, so just the exit status code and the exit code. I don't care how you do it, just make it work. The one thing I do want to say, though, is it's really important that you fully delete processes when they can be fully deleted. Some processes can only really be fully deleted inside of exit, and some processes can only be fully deleted inside of wait PID. And we've got this list of 3 things here. So you can fully delete a process in exit if its parent has already exited. Because if its parent has terminated, and if its parent is a zombie, then the parent cannot execute any code, which means the parent can't call wait PID on you. So there's no reason to keep behind your remains because no one can ever look at them. So get rid of it. If a parent, and so that's for exit. Now, another thing you have to do inside of exit with respect to deleting processes is when you are calling exit, you should look at your list of children and ask yourself, are any of my children zombies? Because if I'm calling exit and I have zombie children, then I know I can't call wait PID on them because I'm dead. Therefore, all of those zombie children I had lying around, they can be fully deleted. So you fully delete them. And then the last one, this is deletion happening inside of wait PID. So if you are in wait PID and the parent has called wait PID, the parent has got your exit status and your exit code, the parent is now done with you and they can fully delete you there as well. So wait PID and exit, you should be implementing them together and keep very careful attention about these 3 different cases where processes can be deleted. Now, one last thing about exit and wait PID, and that is how do you take the exit status code and the exit code and combine them together into a single integer? There is a magical macro in OS 161 called mkwaitExit, and this can take the exit status code as passed to exit and the exit code, which is W exited, and it combines them together into one thing for you. And wait PID is returning the value of this. Now note that mkwaitExit only has a single argument, and that's because it automatically is going to combine with W exited. Now, for the purposes of this assignment, you can always assume we're going to call exit, and processes will not terminate for any other reason, so don't worry about processes being killed or signaled or anything like that. The last thing, of course, is get PID, which doesn't even deserve its own slide, because get PID, return current process as PID. That should be very, very straightforward. All right. So that's the overview of A2a. Before I move on about talking about A2b, what I want to show you is the grading scheme for A2a. So I'm going to go over here. I'm going to zoom in. This is actually posted to our course webpage, and you will note that it lists all of the tests we run for A2a. We have one fork, PID check, wide fork, and fork test. It's out of 30 marks. These are the only 4 tests we are going to run. We will not run any others. There's no secret, no hidden tests. You have all 4 of these tests and their source code. So on Piazza, we are not going to answer questions about whether your output is correct or not, because you can go into the user code library, you can open up the code for one fork and read it, and you should be able to figure out what is and is not valid output. So these are the only 4 tests we run for A2a. That's it. Now, it always happens that somebody doesn't get the system fully debugged. And if you score less than 14 marks or less than 15 marks on the testing, only then will we look at your code. So this assignment's out of 30, but if you get less than 50% on the tests, we will look at your code and see if we can award you mercy marks. Now, these are code inspection marks. They are not added to your testing score. We take the maximum of your testing and the code inspection. And what the code inspection is going to do is we're going to look at your code and see how far you got and assign you some number of marks. It's somewhat subjective. The idea is, though, if you pass no tests but you tried, you don't get 0. So hence why I call them, these are really just mercy marks. All right, so that's A2a, and that's all there is to it. The other thing I want to point out is do make sure you read the hints page for A2a and A2b, because some of these tests, like wide fork and fork test, will actually require that you adjust how much RAM that OS161 is using, and you do that in the sys161.conf, and appropriate values are actually posted in the hints page. All right, so that's A2a. Now let's talk about the next assignment. So, assignment A2b continues from where A2a left off. And in fact, if you don't have A2a working completely, then you won't be able to get very many marks on A2b. It's kind of why it's interesting to talk about these two assignments at the same time. So, fork, wait PID, get PID, and exit, that's A2a. The assignments depend on each other, so you need these 4 functions working in order for us to test your A2b. But the only new code you're asked to implement for A2b is with execv and a function called runprogram. So remember that execv is not creating a new process, but changing the program that an existing process is actually running. And because programs need arguments, we want the ability to actually pass arguments into our new program. Now, again, this is one of those situations where a lot of this code is actually already written for you. All you got to do is copy and paste it. So execv is actually incredibly similar to another function called runprogram. And runprogram is actually how you run and or load and run user programs from the kernel, like from the menu. So execv and runprogram are very similar. What's going to happen is in runprogram, it's passed a program name as a string. It doesn't have any arguments, but you're going to fix that in this assignment as well. And what it's going to do is it's going to open the program. So it opens the program name using vsopen. And then it's going to create a new address space. Now it has to create a new address space because regardless of whether we are changing the address space of the existing process or creating a new process, the process creation does not actually create the address space on its own. So we open the program file, get a handle to it, and then we're going to create a new address space using ASCreate. And then we are going to need to assign the current process this address space. So this is an appropriate time to use curproc.as. Then you'll note that we use this funny function called ASActivate. And you're going to be really tempted to use this in A2a. Don't, because it's one of the singularly worst named functions in all of OS161. This has nothing to do with the address space at all. This has everything to do with a cache known as the TLB and clearing it, which we'll be talking about in a couple episodes in virtual memory. So execv does have to call ASActivate because it needs to clear this cache out. We'll talk more about why that is later in a couple episodes. But you don't need that for A2a. So we've got our process structure. We've opened the program, got a handle to it. We have created an address space and cleared a cache, but we haven't actually loaded the program into the address space. So the next thing that runprogram actually does is it calls a function called loadelf, which is going to load the binary program that we've opened and load its contents into the actual address space. And then once that's happened, we have to create the stack. And we're going to create the user stack calling ASDefineStack. And then finally, to start executing this new program, we call enter new process so that we can actually move the entry point function or the program counter to the entry point. That's run program. And it's surprisingly similar to execv because if you look at execv, And all this grayed out stuff is literally just copied and pasted from runprogram. And in fact, that is my recommendation for implementing execv. Start by copying the contents of runprogram into execv, and then add the extra bits on the end. Now, what's the extra bits? Well, runprogram is called from the kernel, which means that the name of the user program is actually already in the kernel's address space. But execv is called from the user. And so we need to get the name of the program and all of the arguments for our new process or for our new program from the user address space that we're about to destroy into the kernel so that we can open the program and then pass those arguments up to the new address space. So the first thing that I like to do is this step right here. I like to copy the program path from the user space into the kernel. So that's copying from the address space into the kernel's address space. And then I like to count how many arguments are being passed and then copy each of those arguments into the kernel. Then we open the program, we set up the address space, we clear the TLB, and then we call load elf, just as we did before. Then we have a couple things that are a little bit different. We have as-defined stack, but now in addition to creating the user stack, we also need to copy the arguments we copied right here into the kernel, and we need to put them onto our new user stack. So what I like to do is actually create a modified version of as-defined stack and have it actually handle the argument passing, because we're going to need it for runprogram and execv. At this point, we have the new address space completely set up for the new program, so we know that the old address space is not needed anymore, and so we're going to delete the old address space. And then we're going to call enter new process again with a slight change to the arguments to adjust for the fact that we have arguments on our stack, whereas in runprogram we didn't have arguments on our stack. So there you go. Execv and runprogram are actually quite similar. Now, if you're wondering how many lines of code do you have to write for A2b, it's less than 100. It's a really, really tiny number of lines. The next question, or the next part that we should really take into consideration is how do you copy from the kernel to the, or from the user's address space to the kernel, and how do you copy from the kernel back to the user address space? When we talk about virtual memory, you will realize that the kernel's virtual memory and the user's virtual memory are separated. And so we actually need special functions to copy from one to the other. This is probably the trickiest part of this assignment. In order to copy regular things like integers or any kind of fixed size thing, you need to use these functions copy in and copy out. You can think of copy in and copy out as copy in is copying into the kernel and copy out is copying out of the kernel. Now, the kernel can technically directly access addresses in the user address space, but there's a danger with that. The danger is maybe the user address that we've been given would cause a fault, a memory fault. What would end up happening is my kernel would have a blue screen of death and not the process. So what we actually want to do is we actually want to use these copy in and copy out functions so that we can validate that the user addresses that we are using are valid, they're okay, so that we don't get the kernel blue screen of death thing when it just should be the process terminating. So copy in and copy out are used to copy data to and from the kernel that has a fixed size, so integers, bools, things like that. For strings, and all of your arguments in your program name are going to be strings, you're going to use copy in stir and copy out stir. And so long as your strings are null terminated, you can use these two functions to copy strings in and out of the kernel itself. Now, this is the tricky part. It's really tempting when you sit down to implement execv to do all of this work all at once. So you're going to sit down, you'll copy the program name in, then you're going to copy the count the number of arguments there are, copy the arguments in, and then create the address space and copy all the arguments back to the new stack, and then test exec v. And I want to tell you, absolutely don't implement it this way. Don't implement argument passing, which is counting the number of arguments, copying the arguments into the kernel, and then putting those arguments on the stack. Don't even try that until you have 100% of everything else working. It's not so much that copying from the address space into the kernel is difficult, but copying from the kernel back onto the stack is very tricky. And if you get it wrong even slightly, it's impossible to debug. And it's very, very tricky to just work with. So talking about this concept of argument passing, how do you figure out how many arguments have been passed to you? Well, the arguments are passed to you as an array of pointers to arguments, and the last entry is null. So what you're going to do is you need to copy each of the addresses in the argument array into the kernel and count how many you get until you see null. That's going to tell you how many arguments you have. Okay, that's the first step. After you've counted how many arguments there are, then you need to actually copy each of the arguments themselves into the kernel. One of the number one mistakes I see people making at this point in the game is they forget that if you're copying things into the kernel, you need to have memory allocated for those objects in the kernel. So make sure that you're actually allocating space for each of those arguments using kmalloc in the kernel. Now you can use something like strlen to actually compute what is the exact length of each argument, but remember that strlen does not include the null terminator, so you're going to have to do strlen plus 1. That in itself is actually not that safe. It will technically work for this course, but it's not that safe. What I tend to do for this is I count how many arguments there are, and then I make an assumption that the arguments are not going to be greater than some given length, and you can make that assumption. We say right here, can assume that the total length is less than 128 bytes. A TA is not going to sit there, and you're not going to sit there and give arguments that are 300 characters long. Nobody has time for that. So you can make a safe assumption that each argument is a reasonable size. And then just make a big block of memory that is the number of arguments times that size. And then you don't have to use strlen at all. That's what I do. Make sure, however, you allocate all of the space for the strings, the space for the pointers. It all has to be allocated in the kernel, because OS 161 will let you in the kernel write to memory you haven't allocated. And it's amazing. You'll get to assignment 3 and it'll work. And then on assignment 3, when we fix the memory problems with OS 161, it'll stop working. And the errors you will get will blow your mind. The debugger will start randomly running. Or you'll have it try to send a network packet or some ridiculous nonsense because you've overwritten part of the kernel. Oops. So yeah, please make sure you're always allocating stuff before you copy into it, except for those rare cases where you don't have to do that, which is the next part of the discussion. So that's copying the arguments into the kernel. Once you have them into the kernel and you've set up the new address space, then you need to pass the arguments to the new program through its stack. And it's really important how you put those arguments onto the stack. So you can't just haphazardly throw everything on it and say, there you go, go at it. It's a long-standing tradition, not just in OS 161, but pretty much in every operating system and with every program, that arguments go onto the stack in a particular byte alignment. That is that certain types of data live at addresses divisible by certain things. So for example, in OS 161, characters do not need to be aligned at all. A character can live at any address you want. But an integer, well, not an integer, I'm going to have to correct this slide. Pointers have to be 4-byte aligned. What that means is a pointer can only live at an address, and specifically a pointer to a string has to live at an address divisible by 4. A pointer to a pointer has to live at, or an integer or a double or a Boolean has to live at an address divisible by 8. These are expectations that programs have to say, where can I find my arguments on the stack? This is an agreement when the compiler was developed of where are we going to put the arguments and where can the program we are opening expect to find those arguments. Now, to help you with rounding addresses up and down, there's a round up function. And to figure out where the base address of the user stack is, there is another macro called user stack. And I'll show you how to do this here in a minute. Now, you might be wondering, is this something that's really common? Really? Yes, it is. And I encountered the bad side of this once, and it took me a month to figure it out because it wasn't well documented. I was working with Vicom motion capture, and we were trying to take the data from the arms moving around, and we were trying to put that into Unreal to animate the characters. Now, we were using Unreal Engine 3, which didn't use C and C++. It was actually Unreal Script. And Unreal Script could take structures from C, but what wasn't well known was that the structure padding had to be 4 bytes. Everything had to be 4-byte aligned. And by default, Windows programs were not padding structures in C that way. And so when I was trying to get the data into Unreal, I had half my double in one place and half my double in the other, and I could not figure it out. And it was because the alignment, the expectation of where padding was not matching up. And that's why it is really, really important for this assignment you get the padding and the alignment correct. Because if it's off, it's going to be garbage. Okay. So let's look at an example here. So here we have user stack, which is this virtual address right here. Now what I have put on here is I am running the program ls, and I have the arguments -l and Mr. Goose. Now what you'll see is that we have put Mr. Goose, a null terminated string. Those individual characters live at any address. See, they're living here. So we start at this address here, and it goes down there. And there's the argument -l, and there's the program name. Each of those strings are null terminated, and you will note that they live at any address, no alignment required. And then on top of all of our arguments, our program name and the actual program arguments, we have some white space. Now we may have more or less white space depending on how many arguments we have, depending on the length of the string. And then on top of that, we have a null terminated array of pointers to these strings. And you will note that each of these pointers, where they live, is divisible by 4. And the address of this array, null terminated array of pointers, is divisible by 8. That is how you have to put stuff on the stack. Now, when you are putting stuff on the stack, a couple things to note. I recommend that you make a brand new version of AS-defined stack that takes arguments and populates the stack. The reason why I'm recommending you do that is because you're going to need to add argument passing to runprogram as well as execv. So instead of having 2 implementations of the same thing, make one implementation, make it work, and you can call it in both. So make your own AS-defined stack that does this. That's number 1. The other thing that I want to say, and this is a big mistake people make, is everywhere else in the kernel you have to allocate memory before you write to it. I'm going to tell you a secret about the stack. The stack's in AS-defined stack. The stack has already been allocated for you. which means that you just have to compute the address of where something goes and write to it. So you are going to figure out where we start writing Mr. Goose, we subtract the length of Mr. Goose, including the null terminator, from user stack, and then we write Mr. Goose to that address. And then we would have a temporary variable to figure out where -L goes, and it would be user stack minus the length of Mr. Goose minus the length of -L, and that's where the address where we write -L to. So in AS-defined stack, when you are adding your arguments, you are going to be keeping track of where on the stack you are right now, and you're going to compute it, and then you're going to do some math magic and then write directly to the address because the memory is already allocated for you. The hardest part of this is getting the alignment right and figuring out how to write null to the address. Make sure you don't write to null. You want to compute the address where null is going to be and then write null to it. All right. So, we have this list of suggested steps. I've already kind of gone through them. Step 1, copy run program into execv. Step 2, once you have that working, compiling, it's not going to actually execv anything because you haven't passed it a program name, but just make sure that it compiles. Then do the part where you copy the program name into the kernel. Make sure you're using copy and stir, and make sure you actually allocate the space in the kernel for the program name to go. Don't write to memory that isn't allocated. Now, if you're having problems here, and I recommend this as a debugging step, is make sure that after you've copied the program name into the kernel, kprintf it to the screen so that you can make sure that what you've copied in is what you expected. And I know we usually say use GDB for debugging, but you're going to find kprintf's really, really helpful for this assignment here. After you have done that, make the modifications to execv to load the program. Get all of this working without argument passing. So that's like, I'll show you the tests in a moment. That's a good number of the tests. Get them working without args. Don't start argument passing until this works. To do argument passing, you should do this in several phases. In the first phase, just count how many arguments there are. Just count them. And kprintf it in the kernel to the screen to validate that the number of arguments you have counted matches with the number of arguments that you have passed. Once you are convinced that works, then, and only then, copy the arguments themselves into the kernel. Once you've copied the string arguments into the kernel, kprintf them out to the screen to make sure what you've passed matches what you see in the kernel exactly. And only when you have that step functioning exactly correct should you attempt the last part of taking those arguments and putting them on the stack. If you follow those instructions, you will have the best chance of getting this small bit of code to work. I like to say that this A2b is the smallest amount of code you write, but there's about 20 lines of code that will be some of the trickiest code you'll ever write. Now, with respect to the grading, I'm not going to cover it here. I would rather just show you the marking scheme. So let's go back to the course website, and this is the A2b marking scheme. This assignment is out of 50. A2b is out of 50. And 18 of those 50 marks are simply the A2a tests all over again. It is really important you get A2a working for A2b. So 18 of 50 marks just for having A2a working. The remaining 32 marks are for execv and argument passing. Hog Party and Sty do not use arguments. So 18 of those 32 marks don't involve arguments, so over half of them. argtest, and add all use argument passing. Add is argument passing from runprogram, from the kernel, and argtest and argtest are argument passing from execv. So you've got 14 marks for arguments, and you've got 18 marks for no arguments. Hence why I say get no arguments working first. Again, these tests you have all of the source code to, so you can open the code up and run the tests yourself. Now, if you don't get 16 out of 32, so if you get less than 50% on the A2b test specifically, there are mercy marks, but only for the A2b component, just like there was for the other assignment. And if you're wondering, is fork and exit and wait PI used for these? Yes, it is, which is why it is even more important that for A2b, you have A2a working. Okay. So that, in a nutshell, is how to work on A2a and A2b. I will make sure that these guides get posted very, very shortly. So you have this episode, which is number 11, to help you go over A2a and A2b. And if you need a little extra help for A2a and A2b, there's also the fall 2019 A2a and A2b guides, which are on the YouTube channel. And you're welcome to do them as well. They may have extra hints, or sometimes I change it up. It depends on what questions get asked. So you have lots of resources now, I think, to get started on A2a and A2b. Now, on next episode, on Thursday, we're going to start a new topic, which is virtual memory, and that is the abstraction of physical memory from the actual processes themselves, which is going to give us the final bit of isolation we need for our processes. So I will see you all next Thursday. This Thursday. Yes. Thursday.
Thank you.